Hi, and welcome to the section Imitation Learning, where we'll explore the field of self-driving cars and work on an end-to-end method that makes car learn to drive itself. In this section, we'll get exposure into how we can transform an ordinary car into a self-driving car. We start this section by getting introduced to the field of self-driving cars and the state of the art in this field. We'll then have a look at the various sensors and measurements that aid perception and path planning. We'll then explore various architectures for making a car autonomous. And then we'll be exploring the perception stage of a self-driving car in even more detail. Next, we'll see how we can make a self-driving car learn to drive end-to-end just by using a convolutional neural net. And finally, we will be building a project where we train a model to learn to drive a car based on imitation or end-to-end learning. So let's get started. In this video, we'll get introduced to the field of self-driving cars and learn about the various important components of an autonomous system and walk through some examples. In this video, we start by discussing about how the winning of Stanley at the 2005 DARPA Grand Challenge led to exponential interest in building cars that drive itself. Example Waymo by Google. Next, we'll be seeing the various levels of autonomy in perspective of a self-driving car, followed by discussions on the various popular datasets that are used for benchmarking various learning models. We'll then learn about semantic segmentation and its importance in understanding the surroundings. Next, we'll learn about motion and pose estimation with the intent to estimate a three-dimensional motion field of various objects in the scene. And we conclude by learning about tracking, which is useful for tracking the trajectory of motion of objects to help navigate the environment. While the dreams for building an autonomous car or a plane have existed since a long time, the field got more traction when the US Department of Defense, or DARPA, conducted a challenge known as the DARPA Grand Challenge, as a challenge for driving cars autonomously in a predetermined terrain. In October the 8th, 2005, Stanford's robot Stanley finished the course ahead of all other vehicles in a 142-mile-long course in the Mojave Desert, in which about 23 teams raced and only 5 could finish. Winning the Grand Challenge led to Google hiring Sebastian to lead their self-driving car efforts, and Google has already completed millions of miles of testing of its self-driving cars, which recently spin off from Google as Waymo to be part of Alphabet. We will now have a look at the various datasets and benchmarks that serve as a quantitative test for the evaluation of our approach. Datasets are a very critical concern for training self-driving cars because while various algorithmic aspects can be inspected using synthetic data, but to guarantee performance in real-world situations, we need real data sets. Some of the common data sets that are used for evaluation of the approach for self-driving cars are cityscapes, KI, TTI, etc. Due to the complexity of acquiring labeled driving data, and in order to speed up the development of self-driving car research, researchers have started using simulators, example Carla by Intel, and games like GTA 5 for generating driving data more quickly. Now we'll be learning about what semantic segmentation is, which is useful for assigning each pixel in a driving scene a predefined label. The goal of semantic segmentation is to assign each pixel in an image a label from a predefined set of categories. Semantic segmentation is critical for a comprehensive understanding of the surroundings, which is essential for autonomous navigation. Deep cognates have proven to solve the problem of pixel-wise semantic segmentation over a traditional method involving conditional random fields or CR or CRF. Let's see an example of semantic segmentation of a traffic scene in a notebook. Next, we'll learn about motion and pose estimation. Motion estimation is about finding the two-dimensional motion of brightness pattern between two successive images or frames. As we have known, deep learning being able to beat most of the traditional state-of-the-art solutions. A serious limitation of motion estimation using optical flow is that they are not robust to illumination changes. A network called scene flow generalizes optical flow to 3D, that is, given stereo images, sequences in the goal is to estimate the three-dimensional motion field, that is the 3D motion vector for every point on every visible surface in the scene. The estimate of ego motion, that is the position and the orientation of the car, is traditionally addressed using wheel encoders, but they are often subject to slipping, leading to incorrect measurements. In such cases, LiDAR-based odometry is a preferred method for measuring ego motion because 1. They are less affected by changing road conditions, and secondly, they can correct the estimates by recognizing already visited places, which is also known as loop closure. Now we learn about tracking, where the goal is to measure the state of one or multiple objects over time given the measurements of the sensor. Traditionally, tracking is formulated as a Bayesian inference problem, where the goal is to estimate the prior probability density function of a state given current observation. Extended Kalman filter and particle filtering algorithms are widely used models in this context. For an autonomous car, tracking the motion of all the participants in the driving scene is very important. Tracking the motion of traffic participants is a complex problem, and the trajectory of other participants allow us to predict the future location. Tracking in combination with classification of the traffic participants allow the self-driving cars to adapt the speed based on the situation.